So this section is going to start getting into the actual finding antiderivatives and the relationship with the integral. Okay. So let's consider just some random graph. The that's kind of bad. Let me try that again. Okay. If we're looking at from A to B, and I'm going to consider this in looking at properties. Now, remember, if the function is all above the x-axis, the integral from A to B of the function is equivalent. The value of the integral equals the area under the curve. All right. So let's look at these properties. Does it make sense that if I go from A to A, so basically if I start at A and I don't go anywhere, that would be a zero area because my width is zero. So technically, my A minus A is zero, so the integral value would be zero. You want to recognize this. When these are the same value, the answer is just zero. This second one is going to be extremely important. What this says, and what I want you to pay attention to, is these have to be the same in that diagonal. So if I'm going from A to B and I find this area, then I go from B to C and I find this area. Doesn't it make sense? I could just find from A to C, it would be equivalent as A to B plus B to C. So if these are exactly the same in this diagonal, you can just squish this together and go from A to C. Okay. Number 3 has to do with order. If I consider that B is on the bottom and A is on the top, if we flip the order to A being on the bottom and B being on the top, these are just the opposite of each other. So let's come back to this. It's just saying, if I go from A to B this way, A to B is just going to be the opposite if I go the backwards from B to A. And it doesn't matter if we go A to B is the opposite of B to A, or B to A is the opposite of A to B. So if you switch the order of integration, going from B to A or A to B, it just negates the value. A constant multiple, we see this all the time. If you take a function times a constant k, we can just pull the constant on the outside of the integral, calculate the integral value and take it times the constant. And that even includes -1. Sum and difference is really just like the sum and difference when we take the derivative. You just do each one, and if it's plus, it's going to be plus. If it's minus, it's going to be minus. You just take the integral of each one and add or subtract. Max min. This, we very rarely see this, but this is just saying the integral itself has to be in between the minimum value of f times the integral, or times the interval. This has to be in between the minimum and the maximum. That's really all this is saying. The domination piece, I just don't ever hardly see. I will say this I very rarely see, but we're going to see it in the first example. Second example. All right. So let's just look at the basic rules. This is just understanding the general rules. All right. The first thing I want you to pay attention to is it doesn't matter what the function is, or you have to pay attention. This is saying the function f is 5. This is the variable that doesn't matter. But this is only going from negative 1 to 1. This is f going from positive 1 to 4. This is h from, This is h from negative 1 to 1, f from 1 to 4, and f from negative 1 to 1. So you've got to match a lot of different things. All right. First of all, letter A is f from 4 to 1. So we're going to use f from 1 to 4. Since f from 1 to 4 equals 2, if I switch the order of integration from 4 to 1, this is the opposite of this one. Okay? 1 to 4 is the opposite of 4 to 1. All right, letter B. Letter B, we're going to use the additivity. If I go from negative 1 to 1, and I add positive 1 to 4, first of all, I can only add like functions. It has to be the same function. And if I can match this diagonal, not the right color I want, but if I can match this diagonal from one where these are the same, this will be equivalent from negative 1 to 4. So because this has a value of 5, plus this has a value of negative 2, this has a value of 3. Number part C. All right, so this is where we're going to use, first of all, the sum and difference, second of all, the constant multiple. Because I know negative 1 to 1 for both f and h, this is possible. So first we can do f of x dx and separate it with a plus, negative 1 to 1 of 3h. Then because this is a constant, I can take 2 times, so this is the additive, sum and difference, sorry. And then this is the constant multiple. Since this is 2 times f of x, I can pull the 2 on the outside. Because this is 3 times, I can pull it on the outside. This whole integral has a value of 5, so I can replace this with 5 plus this whole thing is 7. So we just multiply our constants and add at the end. letter D is using the order of 0, and I know nothing about 0 in either of these two. So there is not enough information in this particular integral. Now, you would think that this is half, but we don't know that f of x is symmetrical from -1 to 1, so there's not enough information because we don't know anything about the function itself. Same thing for letter E. Even though we're doubling the order of integration, we know nothing about h outside of -1 to 1. Not enough info. Letter F, we could do the additivity rule from -4 to 1 for the function of f, but not for the function of h. So recognizing there's not enough information is just as important as finding the answer. Okay, so example 2 has to do with the max and the min. It's saying show that this is less than 3/2. So if we look back at the max min inequality, in order to show this, we find the max value of f times b minus a. So let's consider cosine. Cosine from 0. Now this is pi over 2, so 3. So this is like 1.1.5-ish. So between here and here, what's the maximum it could be? The max of cosine, the max value it can have is 1. So if the maximum of this is 1, the max of the square root of 1 plus cosine x, if this is 1, is the square root of 2. Because the max of this is 1, 1 plus 1 is 2, square root of 2. So what this is saying is this, if we consider the theorem, has a max of the square root of 2 times b minus a, which is the square root of 2 times 1, or the square root of 2. And the square root of 2 is less than 3/2. This is just 1.4-ish. This is 1.5. Therefore, the integral itself is less than 3/2. So you just look for the maximum that the function can be from 0 to 1, find that value, and then take that value times b minus a, and that's the max the function can have. All right, average value, I am going to star this. Anytime you see the average value, you start with 1 over b minus a, you're really finding the average value of the integral. So you're finding the value of the integral, dividing it by the amount from b to a, or a to b. Okay, so first it says find the average value. So we start with 1 over b minus a. We can actually write average value of f equals, I'm just going to use that, 1 over b minus a times the integral from a to b, oops, actually no a and b, from 0 to 3 of my function dx. always end with dx. Sometimes people get a little confused with this. If you know baseball at all, I talk about pitcher and catcher. The batter is in between. You have to have the pitcher and the catcher. They're like bookends. You cannot have the integral symbol without the dx at the end. These are like a pair. They go together. You don't have one without the other. And when you evaluate it, it goes away. Okay. So if we want to find this value, we have not found, we have not really talked about how to find this value without a calculator. So go ahead and use your NINT. Remember, that's Math 9. So using Math 9, first of all, this is just 1/3. This whole value, when you plug it in, you get 3. And 1/3, what this is doing is saying if this is the value of the integral, I'm finding the average. So from 0 to 3, I'm dividing it all by 3 to get an average value of 1. Now, does f, this function, actually take on this value? So does 4 minus x squared ever equal this value of 1? So first of all, we're going to just set the function equal to the value. So I'm going to move my x squared over and subtract 1 from 4 to get 3. Add x squared. Now, this is important. I'm going to write this up here. We get x equals plus or minus 3, because when we're solving using our square roots, we need a plus or minus. But keep in mind, we are only looking on the interval from 0 to 3. If we would have been looking on the interval from -3 to 0, we'd only consider the negative. But because we're looking from 0 to +3, we only consider the positive. So the actual answer is yes, it does take on this value when x is the square root of 3. Okay, so the mean value theorem, if x is continuous on a closed interval, then at some point c, the function will take on the average value. So theorem 3. And if you need time to pause the video to write that down. Oh. Our last one has to do with if you take, now I'm a really big believer of using inverses. So what do we have for inverses? Add and subtract are inverses because they undo each other in equations. Multiply and divide are inverses because they undo each other. Derivatives and integrals are inverses, just like add and subtract, multiply and divide, derivatives and integrals. Therefore, if I take the derivative of an integral, I just get the original function f. Derivatives and integrals cancel each other out. We really just plug in the x in for the function and get f of x. Okay. And what we're going to start doing is, in order to actually evaluate, When we start evaluating integrals, we find our antiderivative. Remember that was our capital F from last chapter in section 5.2. But I just plug in x into the antiderivative. I plug a into the antiderivative, and I just do the top minus the bottom. And that's how we're going to start finding the antiderivative and evaluating integrals all on our own. Oh, boy, I just didn't erase any of this stuff. Okay, so finding an integral, all of us, up to this point, the only way we've been evaluating integrals is by using area, whether it's the area of a rectangle, the area of a circle. Now we're going to actually use antiderivatives to find integrals. All right, so let's think about what is the antiderivative of sine. All right, do me a favor, because I think you have a review of antiderivatives on the next page. And if you have some open space, let's write out all of our derivatives. Sine, cosine, tangent, cosecant, secant, cotangent. I'm going to move this up. All right. First thing to remember about all derivatives, the cos are negative. Sine is cosine. Cosine is negative sine. Tangent is secant squared. It kind of pairs up with cotangent, which is negative cosecant squared. The other two start with themselves. Cosecant is negative cosecant, cotangent, co, and secant starts with itself, secant, tangent. Notice tangent and secant go together. Cotangent, cosecant, they go together as well. So if these going this direction are derivatives, going this direction are the antiderivatives. So you know what that means? If the derivative of sine is cosine, the antiderivative of cosine is positive sine. Here's where people start getting messed up a little. I know the derivative of cosine is negative sine, so the derivative of negative sine is cosine. But what does that mean about the antiderivative of positive sine? See, if you're going backwards, if you're going this direction, if you're just doing positive sine, you've got to move that negative over. The antiderivative of positive sine is negative cosine. So we're going to write negative cosine x, that's our antiderivative. And then we're going to use our formula, f of x minus f of a. So I'm going to take my top one, capital F of pi, minus the bottom, capital F of 0. Negative cosine pi minus negative cosine of 0. We got to be real careful here with all the negatives. So let's consider the cosine curve. This is 0, pi over 2, pi. So that means cosine of pi is negative 1. I want the opposite of negative 1. And if I have a negative, I'm subtracting a negative. That really is just adding a positive. Plus, bring down this plus, cosine of 0 is 1. Be careful here, the opposite of negative 1. Really, I just have 1 plus 1 is 2. Whew, that was a lot. It's really important to understand this picture. Then you had to know for cosine to evaluate 0 and pi, you had to remember your cosine curve, and you had to be really careful about your negatives. All right, the last slide then is just the review of antiderivatives. So let's think about when we were talking about antiderivatives in chapter 5. Just like we're going backwards, we're undoing each other. Your antiderivatives, the process, the power rule goes backwards. Where we normally multiply and subtract 1, we're going to add 1 and divide if we're talking about polynomials. All right. So capital F of x, the antiderivative of 2x, we add 1. It's got an exponent of 1, add 1. So that's going to be 2x squared and divide by the exponent. Plus 3x plus c. Now this 2 just cancels, so it ends up being x squared plus 3x plus c. When you're doing antiderivatives, everything needs a plus c at the end because we need those constants. Because remember, if you take the derivative of the antiderivative, it gives you the original function. So you can double check all your antiderivatives by taking the derivative to see if you end up back where you started from. All right, letter B. I don't know why some of these are weird. Okay, that looks a little better. Okay. Capital F of x. When I add 1 to the exponent, I get x to the third divided by 3, but then the 3's cancel. All constants become. So think about, we're adding 1 degree to everything, okay? So my degree is 1 higher across the board. Plus c. Don't forget the plus c. This quiz, it'll be really, really important. All right. So when I add 1 and divide, this is the first one where my coefficients don't cancel. I get 2, add 1 to the exponent, and divide by 3. So I'm just left with 2/3 plus c. All right, so be careful here. This time, I don't know, does it help if you think of this as 1/2 x? Because when I add 1 to the exponent, that becomes 2. When you divide by 2, there's already a 2 there. So technically, you're multiplying the denominator by another 2, or just by 2. So that's 1/4 x squared plus c. So you might just turn this off, pause the video, do some of these problems, and then see if you did them right. Capital F of x, add 1 to the current exponent, which is 2, and divide by 2, which is 7/2 x squared. Don't forget, plus c. Okay, this one's kind of sneaky. We have to remember, just like down here, if these are your trig derivatives, there's a couple others. This is your power process for your polynomials. What's the derivative of ln x? Remember, the derivative of ln x is 1 over x. So does it make sense the antiderivative derivative of 1 over x is ln x plus c. So really you've got to think almost backwards. What were these the derivative of? F of x is the hardest one, or g of it, part G, this next one. So do you remember one that had the square root in the denominator? Does it ring a bell that it's going to be one of your inverse trig functions? These are your hard ones. This is sine inverse of x plus c. Because the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. The antiderivative of that is sine inverse. All right, so just like the derivative of ln x is 1 over x, what's the derivative of e to the x? Is e to the x. So that means that the antiderivative of e to the x is e to the x plus c, because we don't know if it started out having a constant. Whew, lots of information, but our big step into finding antiderivatives and evaluating.